As part of this process, we have to develop, research questions, hypothesis to understand and frame in what our research will be. And part of these, we'll roll through them a little quickly, but we'll also understand that these will become part of the framework that we have throughout, the paper to understand exactly what quantum computing is, the current state, and to make sure that we're answering specific questions that pose, considerable threat in information systems today. So, beginning, with the first question is that AES 256 is becoming, weaker and subject to failure due to the impact of quantum cryptography. The infrastructure for quantum computing can be feasibly deployed into the public domain. This includes quantum key distribution that'll provide greater security than the current key distribution methods, as well as quantum-based algorithms that demonstrate the four goals of classical cryptography, including confidentiality, integrity, authentication, and the last leg, which is non-repudiation. The practical deployment of quantum key distribution can be utilized on classical computing. As far as to the extent of what it can and can't do, we have to investigate to see what can be done with the information that we have. The collection and harvesting of cryptographically secure information is being harvested is occurring by our adversaries here in the United States. And the problem of error correction is being addressed in quantum computing to the degree that can be used for deployment. And we'll talk about each one of those as we go along and telling the story, from the beginning to the end. In the early 1970s, we see Diffie and Hellman come onto the scene that indicated that there's a problem with the data encryption standard. In their literature, they write clear warnings to the United States government about the problem, and they are definitely concerned regarding what issues should be done about DES, how to correct it, and we see this go all the way through until about 2005, where the DES standard goes into final retirement in 2005, despite it being reaffirmed and reused by the government. DES is not as secure as it was intended to be, and it failed cryptographically despite those indicators well ahead of time in 1997. In 1970s, Diffie and Hellman had said that they were very concerned about this, even though the equipment is expensive, the technology is expensive now, but it will eventually fall. And in 1997, in the literature, they go ahead and crack the DES standard. So from 1997 to 2005, the DES standard is still implemented and used by NIST at the time, which was NBS, to say yes, we still are going to go ahead and put our seal of approval on DES, but we would recommend you use another product, even though it's still on the slab. So the consequences of this, having DES as the standard, DES was the standard for a long time. It was a sole source from IBM, and that contributed to part of the problem that DES was cascadingly and cataclysmically weaker than its intended and projected use. With being a sole source, reusing those same sole sources is a problem, especially today. You don't want to have all of your eggs in one basket, especially with technology like cryptography. NIST and NSA, and even today with DHS, CISA, they have challenges that where the laws today don't address or detail the technical rigor needed to unify the art and science of cryptographic standards and the infrastructure needed to operate on them. So we see this kind of the back and forth between NSA, NIST, and now the new creature on the block for cyber, which is CISA. And CISA has the ability to, they have a lot of requirements, but they have a short stick to operate by, where NSA, NIST, and IBM are still, tied in as far as, like sole source and that type of stuff. And, as far as the information for, government systems and communications, the NSA's Central Security Service remains the leader, for cryptographic standards, even their procedures and hardware. The government is not, they're to blame as well as far as the activity, not only with DES, but also the way that their networks were set up. The government prioritized and proliferated, to private firms to build their networks in the early 90s. And by, the mid to late 90s, the internet registry is top 97%. So with that, you have privatization of networks, commercialization of networks, and that's where we're at, today. But, the government, they've endorsed another openly accessible algorithm for the protection of even top secret information. And this could be the fuel or the catalyst, again, of another mistake that we see as far as programmatic experience of the government sector moving from more of a human capital and talent development to merely just acquisition. So they want contractors to develop and give us the tools that we need to use it and accomplish the mission at the lowest price. And usually that comes at the, at the expense of human capital, and lower risk taking. So as you move towards acquisition, you don't get greater benefits because the risk of hiring people and doing the mission is less than it would be in the past. I always put, the ability for the government to source human capital from the United States is a huge competition with the private industry, mainly because there's geography is the big one. Washington D.C. is definitely not the technical capital of the entire United States, where Silicon Valley is. Silicon Valley holds 4 technical national laboratories, and then they also have Google, Meta, Alphabet, Adobe, and they have more than 1.4 million technology workers with an average salary of more than $110,000 a year. So that's at contrast with the general schedule of, government workers, benefits, and that type of stuff that needs to catch up to the industry standards to attract those type of people out here, especially in Washington, to help the government out with the mission that they do. But geography is one additional asset in addition to salary and benefits, and as well as, where the crux of the melting pot of the technology workforce is. That collaboration is extremely important, and you've added another boundary, as far as the geography of the areas that these people are in. Our vulnerabilities today are, they're exacerbated by the human capital problem within the government, and also we take a look at a cipher suite like AES 256, taking billions of years now. I mean, mathematically, computed out, it takes billions of years to compute the key. Our enemies really want to steal steal key. It's faster, so they do it with interception. What we want to do is, the United States wants to support, NATO allies and even NATO Tempest standards to make sure that interception doesn't happen. As well as supporting the current infrastructure for that, that top secret environment, the Tempest enclosures, to stop side channel attacks. Specifically, in the literature, the Internet of Things devices are growing. And then also we have one of the presentations that was done in literature is that there was a break of cryptographic keys using an analog to digital chip inside of a transistor radio. So they're showing that this information can leak from a secure environment over to a radio that builds an analog and a digital signal, and they can steal, the cryptographic information directly without having to have the key, in hand. Some of the bigger things that we definitely want to look at is that the investment in research and remaining vigilant as cybersecurity experts and cybersecurity professionals is to make sure that we advocate for the research and development of quantum cryptography, especially with the looming phases of artificial intelligence and the increase in machine learning. We want to make sure that we circle back and advocate for things that we don't want those things to be left kind of in the back burner or in the dust, if you will. Considering how complex, mathematically complex the cryptography is, and it relies on the time-dependent solution of with a brute force. So what of a brute force attack. So what we want to do is we want to make the information that we're sending available to the parties that is secure with in time. So in 1 billion years, regardless of who has it, the information, even if the key was found or decrypted, or if it was broken, the information is no longer useful to the to the adversary. So implementing time is a big thing that we're taking advantage of, and it's still being used today. You know, the early warnings that Hellman and Diffie gave about DES are also becoming true with AES 256 and quantum cryptography. We have to be able to provide an avenue of bringing down, there's an avenue right now where quantum computing is bringing down the calculated billions of years for AES 256 into hours. With higher levels of security, one of the things that we look at is, well, we'll increase, from AES 256 to 512, or, it just depends on what you want to do. Limiting block sizes, we kind of take the standardized approach and say, okay, we'll just increase it to, a block of, from 256, to AES 512 to a block of 256. But a larger variant would need be to be designed and implemented, but it's not really the way you want to do things. It's really to address it this way is to say, okay, we don't want to approach it any other different. We just want to make it more mathematically complex, instead of developing a solution to weakening cryptography. While that's practically or theoretically useful, the implementation of a larger key is definitely not, especially a block of 256 is not a great idea, as far as technical rigor and as well as ethical considerations, knowing that 256 is being reduced to the amount of hours. We'll need some key efforts to make sure that the elements that we're doing today of implementing standards for quantum cryptography will be used for the infrastructure of tomorrow, so we have a little bit more forward thinking. We have solutions regarding factorization, discrete logarithm, and the elliptic curve problems are being solved on quantum devices running Shor's algorithm. We've got quite a bit of activity as far as how to understand the mathematics behind this, and solving those types of problems, and in some cases solving them pretty quickly. The algorithms, they do decompose to primes of very large numbers in time and space, but the nature of quantum systems and cryptography, regarding the observation of the encrypted data, the ability of these systems to interact in quantum states will show you that the data will become, as far as a quantum state will degrade. What will happen is that if you have one quantum state and another quantum state and you separate them, they show that they're linked. But if there's something that changes, that quantum state collapses. And with that instantaneous knowledge of that collapse, that's how we know that data was either viewed or it was changed. And we'll take a look at that in a little bit more detail as we go along. When we deal with quantum mechanics, we bridge two subject area expertise, one in quantum physics and quantum mechanics, and then also in computer science. So as those systems are transmitting encrypted data, we look at the quantum states of each end and determine whether or not they're the same. This is really good. This is really advantageous to us because we have a pre-placed key, a predetermined key, but now with quantum mechanics and quantum cryptography, the key sharing is truly random. In early research, they're showing that the field, as far as the quantum mechanics is concerned, for the keys, they can do it in short distance networks, but not long distance. But also it allows for the detection of eavesdropping early on, which is, that's an implied method of secure communication, saying, hey, if we can detect those instantaneously, we can either close a channel, change a key, whatever we got to do to make it more secure. And every other mix of that type of security and implementation that you can think of can go into that. So there's all kinds of things moving on as far as the literature and the research that's going on today. With the limitations of quantum